Alright, welcome to chapter 2 of this log video series, whatever you want to call it. And today we're going to be talking about vector math, specifically vector math in 2 dimensions. Now, you may not know what a vector is, so let me explain it to you real quick. Let's go to the screen over here, and let's take the situation of your friend, and let's say that he's throwing a ball to you, right? Now, in order to explain the kinematics of this ball's movement using this good old equation right here, if only this would work. There we go. In which we need constant acceleration, initial speed, time, initial position, stuff like that. In order to explain the kinematics of this ball, you need two numbers, the x component and the y component, because as you can see, this has both an x and a y to it, right? So how do we do that? What we do is we pair these two numbers into what's called a vector. A vector can have multiple components to it, but in this case, we're only going to do two. In normal everyday life, you move around in 3 dimensions, right? With another z axis. If I were to draw it, it would be like there's the y, there's the x, and like z's kind of like cutting through it. Woo, cutting through it. But you know this stuff, right? So we're going to be doing math in 2 dimensions. So let's say I'm out on a hike and I'm on the Cartesian plane, right? Let's say I walk 15 kilometers and then decide to walk another 10 kilometers. The path that I took can be described as a vector, right? Because it's like walking in a direction and then walking in another direction. But then you don't know where I ended up because you don't know the direction. So a vector not only has a size to it, which we call the magnitude, but it also has a direction to it, which is described by some angle theta, right? So let's say I walked along this vector, and let's call this vector A. Also, wait a moment. Also, vectors have to be drawn with an arrow above them. I do my arrow like this because it's just easier to write. You know, it's all in one motion, but technically the arrow is like that. Anyways, that shows that it's a vector and has both size and direction. Otherwise, it's just what we call a scalar, and it just has some size to it, right? Most numbers are scalars. This is a vector. So let's say that I walk along the vector A, right? Then I walk some other vector B, right? Just like my hiking trip example, it's just me walking along. I could have done this trip of A and B all in one go if I really wanted to, right? And I could have done... Oh, that's not well drawn. Wait a moment. There we go. I could have done this. And we'll call this vector C. Now, as you can see here, pun not intended, as you can see here, the vector C can actually be written as an addition or the sum of A and B, right? Because, you know, I walked along A, walked along B. It's the equivalent of C as if I had just walked that vector instead. And you can also see here that it doesn't matter if I had done B first or A first, because if I were to redraw this, which actually I won't because it's going to take up too much space, but it would be the same thing because, just like you can write 5 as 3 plus 2, you can also write 5 as 2 plus 3, right? If you had some number line, 0, 1, 2, 3, 4, 5, 6, 1, 2, dot, dot, dot. It taking 2 steps along the line and then 3 steps along that line. Oh, that's not 3 steps. Wait a moment. There we go. There's 3 steps. 2 steps along that line, then 3 steps along that line is the same as taking 3 steps along that line and then 2 steps along that line. See? It's the same thing here. So I walk along A, walk along B, I get to the equivalent of as if I had walked along C, right? Now, what if I scrap all of that? Oh, this is going to be a pain to scrap, but let's say I scrap all of that, right? Get rid of this number line, all of this stuff, and redraw my Cartesian plane. Let's say I walk along some vector A, right? And then let's say I walk along the exact same vector A again, right? And if I were to add these two vectors, I would get a vector that would be, I wouldn't really be able to draw it, but without drawing it above. But let's try and draw it here. I'd get some vector A plus vector A, right? I'd get A plus A. And as you know from basic algebra, however you want to pronounce it, A plus A should technically give me 2A, right? Because when you have x plus x, you get 2x. So, this means that I can multiply a vector by some scalar number, and I'll end up with that same vector just stretched by this number. In this case, I have A stretched to twice its length, right? Now, what if I had, a vector A just as a number here instead of an actual arrow on the Cartesian plane, and I wanted to multiply it by a negative, let's say -1, and I'd have negative A. Technically speaking, if I walked along A, wait, erasing things on this blackboard without destroying the entire thing is such a pain, but I'll try. Boom. If I had some vector -A, it's as if I walked along A and then walked back A, right? Because the negative would just suggest that I subtract by A, and by subtracting by A on a vector, that would just be walking backwards, correct? And so, this introduces the concept of multiplying by a negative. And it basically means that you take the vector and flip it in the opposite direction. Now, what is the result of this A minus A scenario? Vector A minus vector A. Well, technically, 2 plus -2, which is what's happening here, right? It's just A plus -A that's happening here. It gives me 0, right? So vector A minus vector A, or vector A plus negative vector A, Vector A is now going to lose meaning to me. I've said it so many times. Anyways, this should give me some number that's like 0, right? But it's still a vector because I walked A and then I walked back negative A, meaning that you end up with what's called the 0 vector or the null vector. The null vector's job is just like 0's job. When you add the null vector, ooh, that's not a good arrow. There we go. When you add the null vector to A, vector A, you get the same vector back, right? Just like if you go 2 plus 0, you'd get 2. So, what things do we know now? We know that adding vectors is possible. We know that multiplying, ooh, my U looks a little weird there. Multiplying vectors is possible. And we know about the null vector, or the 0. Let's write that out. We know about the 0 vector, right? We also know that vectors have a direction and have an x and y component. Right. Now, forgetting about the null 0 vector thing, that's just another concept that will be used later on. Using adding and multiplying, we can do some interesting things. For example, let's say that we have another Cartesian plane, and I'm going to introduce two very special vectors to you. They're called the unit vectors, and their names are I and J. And this is just a special vector sign to show that they are unit vectors. What a unit vector is it's a vector with length 1 that points along the x or the y axes. It points along some axes. If I had a z, oh, come on, there we go. No, there we go. If I had a z, I'd also have a unit vector k, but I don't. So we don't have to worry about that right now. So we have these unit vectors, I and j, and in theory, you can draw any vector, right? And you can write it as some number into I plus some number into j, correct? Because we know that multiplying a scalar by a vector gives me that same vector stretched. So I can just stretch I, and then I can also stretch j. Then I can add the two together, so stretch I, then stretch j, sorry. I can stretch I and then stretch j, and if I add the two together, I'd get a, right? Because we know that adding vectors is just stacking one vector on top of the other. You go from one end to the other, and then put the base of that vector, of the other vector, on the head of the first vector, correct? And so, you can see that we also have a right angle triangle, but that'll come into play in just a bit. So what we say is that the x component of A into I plus the y component of A into j should give us the vector A, right? Now to figure out what in the world these x and y components are. As I said, this is a right angle triangle, and it has some reference angle theta from the origin, then creates a right angle where the two unit vectors stretched out meet. So using basic trigonometric laws, you can see that ax is just a cos theta. Wait a moment, let me just double check to make sure I got this right. Hypotenuse, adjacent, opposite, SOHCAHTOA. Yep, I got it. Right. a cosine x. I can draw my cos better than that. There we go. And a y is just a sine theta, right? And so now we can rewrite this equation here as a cos theta I plus a sine theta j equals to a, right? And now, using all of these different components, we can solve this problem of the ball being thrown towards to your friend. But I want to do a simpler problem just because it makes it easier for me, right? Let's say we have a building. Back to the good old building. And we have a car. And this car is falling off the building. It's driving right off the edge. Don't know why, and I don't know how it got up there, but I don't really care about those two things. All I care about are where it lands and how long it takes, right? That's all we care about right now. I don't care about how it got there, though I would be interested to know how it got there, because that's no joke, getting a car on top of a building. Anyways, let me just redraw my situation a little better. Excuse me. There we go. And so we can use this amazing equation that we started with in the beginning to solve this. But what we do is that we add in vectors. And I should probably also change the variable name so that you don't think that we're only restricted to the x and y. I mean, to the x in this case. So let's grab that good old eraser of mine, get rid of you, and let's say the position of the car, so let's just say it's p. P, which is a vector, t, equals to at squared over 2a is also a vector, v naught t, vector, and p naught, which is also a vector. I'm pretty sure this is a vector, but correct me if I'm wrong in the comment section. Or I'll correct myself later on in post. So, this car has, like, the motion of this car as it falls off of this building can be described by this magical equation, right? But this magical equation is technically two equations because we're dealing with a vector that has two components. You can rewrite this as px t is equal to at. Ooh, that's not where that squared goes. There we go. At squared over 2 plus v naught t plus p naught. Or rather, px naught. Right. Now we draw our axes. This is our y, right? So we draw that. This is our y, and this is our x, right? So we have two equations. Wait, I forgot to draw the other one. It's the same thing, but with y wherever there is x in the previous one. Let's do this faster. There we go. Now we have two equations that will help us get to the answer to this problem, which in this case, let's make it the time at which it hits the ground. Yeah, let's make it the time at which it hits the ground. So we'll call this time t in seconds, and we say that its initial velocity p. Ooh. Oh wait, v naught x, v naught y. There we go. We say that its initial velocity in the x direction, because it has none in the y direction. It's not flying, it's a car. It's not meant to fly. Planes are meant to fly. So, it has only an initial velocity in the x direction, is 10 meters per second. We know that constant acceleration is just g, which is negative 9.81 meters. Let me rewrite that. Negative 9.81 meters per second squared, right? And that's actually in the y direction, so we draw that. Or on the y-axis, sorry, y is not a direction, it's an axis. On the y-axis, there we go. It's in the on the y-axis, so we say that it's negative 9.81 meters per second squared. Up, meaning that it's actually down, because it's a negative, and negatives flip the direction, right? And there is no sideways acceleration, so as a matter of fact, in our x equation, we can completely scratch this out because acceleration is 0. And in our y situation, we have no v naught y, so we can actually scratch this out as well, which gives us, in the end, px of t is equal to v naught xt plus p naught x, and trust me, this will get even easier in just a sec. Just a hot sec, as people say nowadays. I'll redraw this as g just to show that we are dealing with a situation that is close to Earth. And p naught y. So, what have we not defined yet? We know that we have g. We have v naught x. We don't have t because we're looking for t, right? And we don't have these ones, the ones that have to do with p overall. Well, there are some things that we can figure out. We know that the p naught y at time t, when it hits the ground, is going to be 0, right? So we just say that this is 0. We know that this is 10 meters per second. Also, I am not solving this equation in the most organized way, so bear with me. Negative 9.81 meters per second squared. We have yet to define this one, so let's do that right here. Let's say that the height here is 100 meters. That's a nice number. And we call this 100 meters. We are starting at x0, as you can see here. If I extend my plane a little bit more, you can see that this is the origin, it's x0. So this is actually non-existent, it's a 0. And we actually don't know this because we're going to solve that in a second as well. So in the end, we end up with equations p naught x as a function of t equals to v 10 t plus 0. So it's just p naught t equals to 10t. Px, what am I even saying by this point? Px of t equals to 10t. There we go. And double checking if I'm right. I am right. Then here we have py, there we go, of t is, oh no, wait a moment. It's 0 of t is g t, ooh, I'm not doing variables anymore. Negative 9.81 t squared over 2 plus 100. And those are equations that define these things. Now we get down to solving. Right? Just double checking here if I missed anything. I have t, the y at this point is equal to 0 meters. I have some x. I don't know what it is. No initial. Gravity is correct. I have the y. Initial y value. Yep, I can solve this now. So, first off, let's start with this one because it only has one variable. Over here we can see that we have px and t. So we figure out how long it takes to hit the ground by solving this one. And let's rewrite it over way up high. That way I have more space to work with. Here, 0 as a function of time equals to negative 9.81 t squared over 2 plus 100. No, plus 100. And then you do the good old algebra stuff. 0 as a function of time is just negative 100 equals to negative 9.81 t squared. Negative 200 equals to negative 9.81 t squared. 200 divided by negative 9.81, and you can see the negatives cancel here, so it does make sense. T is not a negative in this case because time has been moving forward. Equals to t squared, then you take the root of both sides and you get this thing. T equals to negative 200 root negative 200 over negative 9.81, and I can probably just cancel off the negatives. Right? Then I'm not going to solve for that because I don't have my calculator ready, but I can just put the result of that equals to 10 into root this thing, and we're able to solve the specific case of a car falling off of a building. Now we figured out the two things that we didn't know in this situation, which are what the time at the point of landing is and where does it land. The two things we started with. And this is all using vector math because originally we had this equation which is done as a vector, meaning it has two parts, an x and a y. Then you solve it up, and that's vector math for you. This is not all of vector math, by the way. I will have a part 2 to this video because there's also angular motion and stuff like that where you have the situation of, let's say, your friend throwing that ball. When you have your friend throwing that ball, it's actually got much more to it because you have the max height here, you have the point at which it hits you or you catch it, and more stuff like that which require more math, which I'm going to explain in another video. So yeah, if you're confused by this, that's probably because of me not explaining it too well, because, things happen. But this is it for now. Part 2 will be coming soon. And go watch my other videos if you were confused by the whole magic equation thing. I explain it really well in those ones, actually. Those ones actually make sense. Don't make this your first impression of me. Go watch the other ones. And yeah, bye.